In this lesson, we're going to be looking at a sliding bar on conducting rails in an external magnetic field, and this is the basic premise for how a railgun works. So how can we use current and a magnetic field to actually accelerate this bar? Well, we definitely need a current, so we definitely need a power source. So that's our battery. Let me zoom in here. That's our battery here, driving a current. I'm going to use conventional current now, down the conducting rail, across the bar, back down the rail, and then completing the circuit. So there's our current. We have an external magnetic field, in this case oriented downward. And to solve these problems mathematically, you definitely want to use a cross-sectional view. So you want to look at it from standing in front of the bar, and that is the view that I have shown over here, where the current is into the paper. So that's our blue current into the paper. The magnetic field, right, is straight down in this, from this view here, right? And we are going to look at the magnetic force. So we are going to look at IL cross B. Now, the cross product is sine of 90 degrees between the current going across the bar L. So L is the length of the bar. So L will always be the length of the bar in the IL cross B for sliding bars. And we get ILB because we have sine of 90 degrees. And when we do our right hand rule, our right hand, again, confirm this, I is into the paper. Curl your fingers down, thumb to the left. So the magnetic force, ILB, is going to be to the left. So the magnetic force, ILB, right? ILB. Well, we of course have mg, straight down, force normal, and we don't have friction in this problem, but just to remind you of our mechanics problems, and that's really what this is boiling down to very quickly, a mechanics problem. If you wanted to consider friction on the rail, we would have mu force normal opposing the F sub B to the left. Now, in my Newton's second law, F equals ma, I'm going to look at the y direction. Sum of the forces in the y direction equals mass times acceleration in the y direction. I'm assuming that it's not sinking in or popping up off of the rail, so that's why acceleration in the y direction equals 0, force normal equals mg. That is what we've always had. Now, in the x direction, it depends whether friction is given to you or not. Without friction, the only force is the magnetic force to the left, so that's the negative ILB. And of course, if friction was to the right, we would add in here, and you put it into your notes if you want, or not. It doesn't matter because this is just an example problem. But we would have plus mu times the force normal if friction were added to the problem. Okay, the only other version of the rail gun type problem, or the sliding bar problem, is if it's put on an incline. And again, this very quickly boils down to a mechanics problem. So we have the same situation where we have our battery. So let me zoom in over here for a moment. We have our battery driving a current I up the rail, across the bar, down the rail, completing the circuit. So what we have then in our cross-sectional view, we're going to be, again, looking in from standing in front of the bar as the current is going away from us. So that is why I have the current drawn in the way that it is here. The current is going away from us. Now, in this problem, we were told the magnetic field is going vertically up from the horizontal. Now, it's still a bar sliding on an incline, so we are going to rotate our coordinate system. We are going to put in mg, and if you remember from mechanics, the block on the incline, mg sine theta is going to pull it down the incline. Mg cosine theta is going to push it into the incline. I'm working with my rotated coordinate system. Now, the magnetic force, IL cross B, still has 90 degrees, just like the above problem, still has 90 degrees between I and B. And this is by far the biggest part, I think, that is hardest to visualize initially. Now, if you use your pen to point straight down into the page, that's the current. So the current's going into the bar, and B is straight up in the page, and there's your 90 degrees. So when you do your right hand rule, your right hand going into, piercing into the page, following the current. Your palm is now facing the top of the page, so it's a little bit contorted. Curl to make a fist. Your thumb is now to the right. And that is the ILB we have here. Now, that ILB is not on my rotated coordinate system, so that is why we have force B sine theta and force B cosine theta, and of course the force B is ILB, and we have a force normal pointing straight up because the bar is not sinking into the rails. Now, in the y direction, Newton's second law, sum of the forces in the y direction equals mass times acceleration. We do have to be careful because we now have the force normal. We have mg cosine theta here, but we also have the FB sine theta over here, pointing up. So that's pointing in the same direction as the force normal. So that is why that is up. Force normal is up, and mg cosine theta is down, and we're still assuming that it's not sinking into the rails, so there's no acceleration in my rotated coordinate system y direction. Now in the x direction, we have sum of the forces in the x direction equals mass times acceleration. We have mg sine theta down the incline. To the right is my positive x direction. So let me erase some of this. So my positive x direction is down the incline in this case, my rotated coordinate system. So I have plus mg sine theta down the incline. Notice we also have FB cosine theta now down the incline equals mass times acceleration, and that acceleration is down the incline, and we have ILB. And of course, if you added friction, friction would be parallel to the incline and up the incline, and that would subtract from our x direction force if friction was given in the problem. So there you have it. It's the basic premise. A lot of this was, I hope, review of mechanics. But if you are given this type of a problem, you can refer back to this page of notes for the sliding bar and how to analyze how the magnetic force will affect the motion of the bar.